Today we're looking at Monte Carlo simulation in Python. And maybe you've never heard that term before, but what Monte Carlo means is we want to simulate a real-life experiment using random variables on a computer. Now, what are the advantages of that? Well, of course, when you're on a computer, you can run many experiments, whereas in real life, maybe it takes a long time to run an experiment, and so you're sort of bounded by time in the real world. Monte Carlo can also be used to generate some beforehand experimental results to make sure that your experiment that you're actually doing properly and that it matches up with what simulation should tell you. This video is a really basic introduction to Monte Carlo methods, mostly about how to generate random variables. You know, sometimes you have a distribution that's not coded into Python. How then do you generate random variables? And then also how to set up an experiment, right? You're given something that's going on in real life. How do you actually use those random variables to conduct an actual experiment? Be sure to like and subscribe if you enjoy this video. Check out all my other videos as well, and enjoy. As always, for packages, we got NumPy, SciPy, Matplotlib, SymPy, and I'm going to use the nicer plotting style for Matplotlib. And so before we get into any coding, it's useful to give a little bit of an introduction for what exactly Monte Carlo is and what the purpose of it. And so I would say, and it's defined in slightly different ways depending where you look. So I think the easiest way to express this is as follows, what I have written: to simulate a real life experiment that depends on randomness to some extent. So when you do experiments in real life, whether you're, measuring particles in the Atlas detector or counting radioactivity from a source, there are elements of randomness that happen in such a thing. So for example, like I say here, counting number of radioactive decays from a radioactive source, and suppose you're counting for 10 seconds. Well, that's a Poisson random variable. And so it has a probability mass function that looks like this. So this is just a standard statistics. You may have seen this before. So if I plug in a value of x, this gives me the probability of that many counts. So if I plug in x equals 1, it'll return a value x equals 2. And lambda is the mean value. Lambda doesn't have to be an integer. It could be a, real number, for example. But I plug in x, which is an integer here, and it returns for me the probability. That's what a probability mass function does. Another experiment, maybe you want to determine the energy of detected particles in a particular detection cell in Atlas, which is a huge thing about what my master's thesis was about. And so here the random variable, the thing that's random, isn't the number of counts anymore, like the Poisson distribution, but it's the actual energy that's deposited in the cell. So the energy E is the random variable now, and the corresponding probability density function looks like this. So this is different than the probability mass function. The probability mass function, it gives me a direct probability. The probability density function, 6x, is continuous here. It's not just the number of counts anymore, 1, 2, 3, 4, 5, 6. It's continuous real number. I have to integrate this function between two different values of x, and that's how I get the probability. Just like a density, if I want the mass, I integrate the density over some space. So if I want the probability, I integrate the probability density function over some region of x. So this is my probability density function here, and we'll get into that in the video. So this is actually a good model for the Atlas liquid argon calorimeter. This is a model that I used in my thesis, and it represents things really well. And there's particular values of F1, E1, F2, and E2 that you would fit to some real data that you measure. There's another example here you can look at. And then, of course, a really famous Monte Carlo simulation that's really easy to do in Python is you can actually estimate a value for pi. I probably won't do this in this video, but there may be an upcoming video, a short one, where I show how to compute pi really easily in Python. Because, pi is an interesting number. As a concept, it existed for a long time, but as an actual value, the 3.1418, whatever pi is, that's not so trivial to come up with. So for most cases, when you're simulating an experiment, there's two essential steps here. You want to generate random variables according to a distribution, maybe a Poisson variable, it could be a variable that looks like this, or any other thing that, is relevant to your experiment. And you want to use these random variables to conduct some sort of experiment. And that's sort of vague how I've said it right now, but I'll sort of go through 1 and 2, and I'll go through everything and I'll show you how this is sort of done. So the first step in all these things is to actually generate random variables according to a specific distribution. And that's not as easy as it always sounds, right? I mean, you know that computers can generate random numbers. They can generate random uniform numbers. And if you have a package like NumPy, it can generate lots of different types of random numbers. But suppose you have a distribution that's not in NumPy. How would you actually generate a random number according to a distribution? And there's a really useful theorem here, and this is the most important theorem, I think, for Monte Carlo. And it's really useful to sit, read it, and really understand it. So it goes like this. If a random variable x, so x is the random variable here, has a cumulative density function f of x, that's useful to know what that is, the CDF. So the probability, that's the integral from negative infinity to x of the probability density function in the case of simple distributions. So if x has a CDF of f, that's unique. If you know little f, you know big F, so they're equivalent to each other. Then the variable f inverse, so the inverse function of this function, u, where u is a random uniform variable between 0 and 1, also has CDF f of x. So that's a lot, and I've written it really simply here. So x, this means distributed according to f of x. That implies that f inverse of u, where this is a random number, uniform between 0 and 1, also has this distribution. So this x and this both have the same distribution. So that's a really useful tool. If I can generate lots of u's, a lot of numbers between 0 and 1, and I plug them into f inverse and I compute numbers, they'll be distributed the same as x. So this is the key result that sort of all Monte Carlo is based on to some extent. So for example, let's look at the exponential distribution. Here the probability density function is equal to lambda e to the negative lambda x. The cumulative density function, which is the integral of this from negative infinity to x, is 1 minus e to the negative lambda x. So this is what capital F of x is. Suppose I want to generate random numbers according to this distribution. Well, we can do that. And before we do that, let's actually look at f, little f and big F. So here I make some x variables from 0 to 3 to 100. Let's import the packages here. So here I just make 100 things between 0 and 3, and I'm just plugging in little f and big F. And here lambda is equal to 2. So let's actually plot these functions, right? And so I have x and f and x and big F. And you can see that little f of x, it looks like this. There's more probability of, whatever being in this region, of x being here, and then less of it being here. And then capital F of x, which is the cumulative density function, it goes between 0 and 1. This is like 100%. So if I go here, this is the probability that, the random variable is less than or equal to this value. So if I'm way out here and it's 1, you're basically 100% that it's somewhere in this region less than that number. That's what the cumulative, the word cumulative, right? Cumulative density function says. So these are what these functions look like. Now, in order to compute f inverse of u, which is going to give us our random exponential variables, we have to compute f inverse. So, there's a simple way of doing that with math. I use f of f inverse of x equals x. That's the identity here. Then I plug f inverse of x into capital F. So 1 minus e to the negative lambda f inverse of x equals x. That's just this formula here, but plugging in what I know capital F is equal to. So this is useful for that. And then I solve for capital F inverse of x, and I get this formula. F inverse of x equals minus ln 1 minus x over lambda. So this is what the inverse function looks like. So if I generate a bunch of u's and I plug them in here, what the theorem says is that they're going to be distributed according to an exponential distribution, right? So I'm going to make a bunch of u's, I'm going to plug them into this function, this weird looking function here, and they're going to be distributed exactly how I want. So that's what I do here. So here I'm generating 10,000 random uniform variables between 0 and 1, and I can make a histogram of them just to prove this to you. And let's show this here. You can see that these are random uniform. That's how I call this in NumPy. And it's about uniform between 0 and 1. You can see that they're distributed like this. So that's sort of exactly what we want. And we're going to use those to generate these capital F inverse of u's to get exponential distribution variables. So I call this my F inverse u's, which is plugging in u to this function. And I just plug in all these values of u's into this function here. So I evaluate them, and now I'm going to make a histogram of this F inverse of u's. So what I do here is I'm looking at, so first two things. There's the probability density function here, F, blue. I showed that above here as well. And you can see that I have a histogram of these random variables, and I've normalized the histogram, density equals norm, so that the area under the histogram equals 1. just like how the area under f of x equals 1. If I didn't have this here, for example, if I deleted this, which happens a lot, here you can see that this is really small and it's counting the number of occurrences. So I want to make sure that my histogram is normalized per se. So I go like this. And so you can see my f of x, which is the distribution I want to be distributed according to, and my f inverse of u's, right, which the theorem says should be distributed according to f of x, right, and have a CDF capital F of x. You can see that it follows it exactly. So I have a really good method now for generating random variables. So there's a little bit of a fly in the ointment, and I'm sure you've maybe thought about this when I was going through the previous step. Well, what if capital F of x isn't actually invertible? What if there is no f inverse of x? Well, let's think about that for a sec, because we know that capital F of x is always increasing with x, right? If I look at this plot here, I know that the probability of being less than or equal to this is going to be greater than the probability of less than or equal to this just because I have more stuff, right? So capital F of x is always increasing. This is true for every distribution, right? And so if capital F is always increasing, there's necessarily an inverse. It doesn't mean that there's an analytical inverse, like a formula that we can actually solve for, but it is necessarily invertible, right? Unless, of course, it's constant and then maybe you have a discontinuity, but it's basically invertible is what I would say. A mathematician might get mad at me for saying that, but it's basically invertible. And so, for example, look at this formula here. This was the distribution of energy in an Atlas calorimeter cell, for example. So it looks like this. So let's actually plot this distribution before I get into the example, and the cumulative distribution as well. So here I'm using SymPy to actually come up with the formula. I want to find the CDF, which means I have to find the integral of this. And rather than do it by hand or show you a bunch of mathematical steps, I'm just going to do it in SymPy and show you the power of SymPy, as I always do. So here I define x and y, and then the four variables here, f1, f2, e1, and e2. They're both real and positive for this distribution here. And I define my f, and s stands for symbolic. So if you see a s after a variable, it means I'm dealing with a symbolic thing. So my symbolic function looks like this. f1 times simp of this, it's just this formula in SymPy. And I can look at it, and I truly do get this formula. And if I want the cumulative distribution function, well, what do I need to do? I need to integrate this function here, which is f symbolic. And I want to integrate x from 0 to y. Now you might be wondering, why am I going 0 to y? Well, I can't use x twice, right? So I'm going to go from 0 to some other variable that I'm going to call y. So I integrate my symbolic probability density function to get the cumulative function using SymPy. I call this, and then lo and behold, I get my cumulative density function with y instead of x here, but it's really the same thing. Y is the variable that's interesting here. So it's a big long function. Now the issue is, right, we want to compute f inverse here, but I don't really feel like taking the inverse of this function. I don't know if there really is an inverse. There might be, not as far as I know, to this function here. And so what we want to do is we want to find another way to take the inverse of this function, sort of using a computer. And I'll show you the sort of trick here. So the first thing we'll do is we'll convert this function here to a numerical Python function. So that's n here. Whenever you see an n, that means a numerical function. It means I give it numbers and it returns a number in Python. It's a normal function. To do that, I have to Lamdify the symbolic function. You've seen this in my other videos. These are the input arguments. This is the symbolic expression here. And this will turn it into a numerical function where I can actually give it arguments. So I can run that. Here I have a numerical function for the cumulative distribution function and the regular probability density function. So I give it some sort of numbers here, e1 and e2 are equal, and then two different values of f1 and f2. And I'll plot it between 0 and 5. And so here I'm actually obtaining values. There's no n or s. These are actual values for f and capital F. So I'm going to plot this function. I'm going to plot both the density function and the cumulative function here of these two functions. So you can see little f of x, the distribution looks like this. So there's a lot more chance of getting lower energy and then less chance of higher energy. And it's not quite exponentially decaying. It's sort of decaying in this, square root exponential fashion with like two different terms here. So like I said, clearly capital F of x is always increasing, right? You can see it's always increasing like I said it would for most distributions. But inverting the formula is really difficult. And so how can we approximate f inverse of x given the information that we have? Well, it turns out you can do it in this one line here, and that's obviously really fast, and I'll explain it. But here's what we do, and this is essentially what's going on here. So I take my capital F, and I go from the literal numerical values that I've plotted here, right? That's what the capital F array is. And I go from the first point to the second last point here. So those are all my values, right? And I call this np.searchSorted on this array of all these values and all my random uniform numbers as well that I've generated. And so what that does is it says, okay, well, I know the u's are between 0 and 1, right? So they're sort of here like this. And so I have u is equal to 0.2, for example. What np.searchSorted will do is it'll look at this array of f values, and it'll give me the index, so not the x value, but the index of this array, where the u's would fit in between to keep this sorted. So what it means is that it'll essentially find the index where if I were to insert this value of u, maybe 0.2, into this array, given that this is always increasing, what would be the index I would have to insert it into to keep that array indexing? So if I had like 0.1, 0.3, 0.7, 0.9, and I was giving a value of 0.4, I know that 0.4 would have to come after 0.3 and before 0.7, right? And that's the index. So I would find the index of that, and that's the index it would return. And so that's what's going on here. So it gives the indexes here. And if I want the x value, I just call x, and this would be an array of indices, right? And so to give me the x values at all these different indices here. And then I have the x's that I want, right? This is what the inverse function is. It says, give me the x value such that this is the y value. So if it's like 0.6 here, it's saying, give me the x value such that y is equal to 0.6. That's what this essentially does here. So again, if you're still confused, I'd recommend looking at what np.searchSorted actually does. But this is computing the inverse function. It says, give me the x value such that, 0.2 is the y value, right? And that's sort of what's going on here. So I can compute my f inverse of u's in this way. This is the numerical way of doing this. And I can plot them just to make sure that it is indeed that these values are distributed according to little f, which is the probability density function. And you can see indeed that they are. They sort of match up here. So the thing that we did worked really well. So finally, of course, there's built-in random variables in NumPy. Like, you don't always have to do this thing every time you want to generate a certain type of random variable. So here I'm looking at the Rayleigh distribution. It's a particular probability distribution, and there's tons of others in NumPy as well. And so here I can generate a bunch of random numbers, and I can plot them, and you can see that they're distributed according to a certain distribution here. And there's lots of other functions in numpy.random. And so we can actually look here at all the different types of functions. And you can see if I scroll down, we got beta distribution, binomial, chi-squared, exponential, Fisher distribution, gamma, geometric. So all of these are available to you. So if you're doing an experiment and you want a particular type of random variable, definitely make sure that it's in Python and NumPy first before you go and try to invert a cumulative distribution function and generate things that way. So there are lots of built-in functions, and then even probably extensions of these in other packages in Python as well. So before you do the other steps that I did, unless you have your own distribution that's a little bit unique, look to make sure it's in NumPy, and then you can just generate a bunch of random numbers like this in a one-liner. So now we get to part 2, and that's actually using these random variables to conduct an experiment. And I sort of left that a little bit vague before, and I'll go over an example, and hopefully that sort of makes you understand what this really means. And so let's sort of go over this. So suppose the amount of particles that enter a detector in a 10-second interval is a random variable x with distribution this. So it's a Poisson random variable. So I count for 10 seconds, and maybe there's 5 particles one time. Then I count for another 10 seconds, and maybe there's 7. And then I count for another time, and maybe there's 13. So it's a distribution. So my experiment is counting the number of particles that enter the detector in 10 seconds. Well, that's one part of the experiment. The energy deposited by each particle is a random variable, capital E, that has this distribution. So that's the distribution that I went over before. So there's a random number of particles being, detected in the detector, but each one of those particles itself has a random energy. So you can see how things start to build up in these experiments, right? And so what I'm interested in here is in a 10-second interval how much energy is deposited in the detector. So I have two random variables that I'll need to distribute. I'll need to sort of combine them together, and then we can sort of simulate this 10-second of energy deposition in a detector cell. So the parameters here are lambda equals 4. That means the mean number of particles in 10 seconds is 4 particles. And then I have some values for F1 and E1 and E2 as well here. So I know this distribution. I know this distribution. Let's find out how much energy is deposited in a cell in 10 seconds. And you might wonder, well, why are we interested in this? What's the point of this? And it could be that you're designing a detector cell and you have to make sure that not too much energy is deposited, or maybe it will break down or whatever. So these sorts of simulations are really useful. And believe me, it's all the time used in all experiments. In fact, the entire Atlas experiment has an entire simulation side to it, just to check for things like this, to make sure that things will run well and that things agree with true experiment as well. So let's do 100,000 experiments of 10 seconds each. That'll give us a lot of statistics. Like obviously in real life you can't do this, and this is the nice thing about Monte Carlo, is I can generate 100,000 experiments of 10 seconds each. So here n is 100,000. I'm going to generate 100,000 Poisson variables with lambda equals 4. So for each experiment, that will tell me how many particles are detected in a 10-second period. Now, I need also the random energy of these particles as well. So if there's maybe 4 particles and then 3 and then 8 and then 7 and whatever, over 10 or over 100,000 experiments, there's going to be more than 100,000 particles detected. It's going to be the sum of all these. So I need to generate more energies, of course, than 100,000 because there's more particles than 100,000. So this is part 1, the Poisson, and part 2 is going to be the energies. So here, I need to use my special way of inverting the function, which is what I do here. And the number of U's that I need to generate, remember, a bunch of different random energies, is the sum of all the particles, which is just x dot sum. So I'm going to generate however many there is of this, and then I'm getting my random energies using this inverse thing that I talked about in part 1 of the experiment. So I run this, and so now we have all the random variables that we need. And so now for each experiment, remember the first experiment, maybe there was 2 detected, the next one maybe 3 detected, then maybe 5 detected. We need to determine how much energy there was in each one of those experiments. And so there's lots of different ways that you can loop over things and add up the energies and whatever, but I'm going to give you a kind of a clever way for how to do this. So the first thing I want to do in this clever way of doing this is we're going to get a net sum of how many particles were detected after n experiments. This is like a cumulative sum. So if I look here, it says after 0 experiments, there were 0 particles detected. After the first experiment, there were 2 particles detected total. After the second experiment, there were 6 particles detected total. 3 experiments, 12, 17. So it's a cumulative sum of, after that many experiments, how many total particles have been detected. So then what we can do is we can actually use these values here to sum together the energies over various experiments, right? And so these are the first 10 energy random variables that I have. But if I know that I have 2 particles detected after the first experiment, I would sum these 2 together, and that would be the first experiment. Well, then 6, right? I would need to sum the next 4 together. So I can use this array to say, all right, well, 0 to 2, I'm going to sum these 2 elements together. 2 to 6, I'm going to sum the next 4 together. 6 to 12, well, I need to sum the next 6 together. So I use this array and the array of energies to get the total energy for each experiment. Really think about that, because this is sort of tricky. And I can use this np.add.reduceAt with e and index. So it will sum, consecutive elements like this. So it'll sum the 0 to 2, it'll sum these together. That's the first element of the new array. 2 to 6, it will sum these 4 energies together, right? That's the second experiment. There were 4 energies, and the elements in this array, this index that I generated here from x, which is the number of particles, is the sum of these 4 energies, and that gives the total energy, and then on and on. So that's what reduceAt does in Python, in NumPy. So I can run this. Let's actually run these first. So I have my indices, which is the trick. I have my energies. It will sum the first 5 energies together, and that's my first experiment, the total energy for the first experiment. The next experiment, 5 to 6, well, it's a cumulative sum, so there were only 1 particle detected in the next experiment. So the first experiment is all these energies. The second experiment will just be this energy. And then 6 to 10, well, then I need the next 4. Hopefully it makes sense. I've repeated it a few times now. So gives me my E every 10 seconds. That's my array here, like this. Now let's actually make sure it's doing what we want it to do. So remember that the first experiment, there were 5 particles detected. So it's this plus this plus this plus this plus this. And this equals this number. And that's the first 10 seconds of the experiment. Well, the next one, 5 to 6, there was only 1 particle detected. And indeed, 2.08 is the energy that I get here. Now let's make sure, well, let's see what this distribution looks like, is what I plot here. So this is what the distribution of energy every 10 seconds looks like. This is a histogram. So you can see it's sort of flat here. So there's almost a flat region where, a lot of these are between maybe, 0 to 3 GeV of energy of particles. And then you sort of have this tail here that goes like this. And so we've conducted an experiment. We've said we're going to look at every 10 seconds. Our experiment is 10 seconds. How much energy is deposited in the detector. And we get this unique looking distribution that probably doesn't have an explicit formula for it. Or if it does, it's probably very complicated. So we have a distribution that looks like this. Now, having run that Monte Carlo, we can then, determine interesting things, for example, right? So for example, let's look at how much of this histogram is, above 7.5 GeV of energy, because maybe we really don't want high energy deposited in a detector cell every 10 seconds because the detector, maybe there's a certain amount of material that can be ionized and it needs to refresh or whatever, so you can't have too much energy. So if I look at the proportion, like how much, is in this region, I'm just summing up, how much of these are greater than 7.5 divided by the total number of events. And you can see that there's about 5.22% of things that are above 7.5. So what it means is that 5% of the time we expect more than 7.5 GeV of energy. And this could be useful when actually planning like the materials you need for the detector, what it sort of needs to compensate for, and all things like that. So this is a little bit of a taste of what Monte Carlo is and really how it can be useful in experimental planning. And in the Atlas experiment, like I said, they have an entire simulation and then the entire physical experiment, and they'll actually compare the results of the two to determine things like new particles, for example. Anyways, I hope this video was useful. Be sure to check out all my other videos as well. There might be a short video in the future about how to compute pi, the actual value of pi in Python, using no beforehand knowledge of pi, just using random variables. Anyways, thanks for watching, and I'll see you next time.